Hi everyone, this is Myriam Neaimeh from the Alan Turing Institute and Newcastle University. Welcome to the Smart Charging webinar series. Today's talk is on ISO 15118, a communication protocol between an electric vehicle and a charging station. The aim of the Smart Charging webinar series is to find out who is doing what on electric vehicle charging infrastructure, with the objective of, when possible, collaborating in the development of a fit-for-purpose EV charging infrastructure. This is especially relevant right now in the UK to know who is doing what on smart charging because of many electric vehicle policy developments happening. Notably, in 2018, the UK government passed the Automated and Electric Vehicle Bill. And this law gives government powers to introduce additional regulation. And in 2020, we are expecting to see the additional regulations introduced, as you can see on the right-hand side of the slide. Now, in between 2018 and 2020, there is a consultation process that is taking place. And in the consultation document, the government proposed measures and asks the feedback on these measures. Right now, government is analyzing the responses, and the output of this consultation will inform the new regulation on electric vehicles smart charge point regulation 2020. In parallel to the laws being developed, government is proposing that smart charge points will be required to comply with the British Standard Institution standard on energy smart appliances that includes electric vehicle charging. Now, the regulation are mandating that all chargers must have specific requirements to ensure that the government policy principles are met, specifically grid stability, cybersecurity, data privacy, and interoperability. Now, when we hear about interoperability, my stance is that this implies open protocols such as ISO 15118. Now, interoperability, underpinned by open communication protocols, would allow successful electric vehicle charging management strategies. And I wanted to give a brief overview on e-mobility standards and where ISO 15118 fits. Now, there are several energy and mobility entities involved in smart charging, and they need to exchange information and control objects to allow these strategies to take place. And communication protocols provide a set of rules to facilitate this exchange. And open protocols would facilitate this and would ensure interoperability. Now, on the graph, there are several protocols that could be divided into back-end protocols, and these are linking the electric vehicle supply equipment or charge station to an operator, such as charge point operator or an aggregator. And an example of a back-end protocol is OCPP. But also there's the front-end protocols linking the electric vehicle supply equipment to the car. And this is where ISO 15118 sits. Now, the front-end protocols, so linking the car to the charging station, can still be divided into low-level communication and high-level communication protocols. So for example, IEC 61851 is a low-level communication. It's a cross-cutting standard across charging topology, safety, and communication, but low-level communication, as it does not allow advanced data exchange, such as meter readings and tariff information. And this is where the high-level communication protocol, ISO 15118, comes in, which allows this sort of advanced form of communication. Now, as part of this webinar series and speaking with experts such as Marc, I am interested to hear if it is possible to achieve interoperability without open protocols, but also what is required to drive the adoption of open protocols. For example, do we need legislation to ensure that these open protocols are adopted? but also specifically to this webinar is what resources are required to implement a protocol such as 15.11.8. On this webinar, we already spoke about OCPP, OpenADR, and today we're speaking about ISO 15.11.8. We also spoke about real-world demonstrators using these open protocols to demonstrate that they can successfully carry out smart charging strategies with open protocols. The slides and the videos of those webinars are available on our Smart Charging webinar landing page. Upcoming events will give a policy overview, but also regional developments, such as in California and in Denmark, rather than specific projects. And it will also be followed by a webinar on another protocol called IEC 63110. Two more slides from me. The Smart Charging webinar is an activity of the Supergen Energy Networks Hub that is led by Newcastle University and by the Vehicle Grid Integration Group at the Alan Turing Institute. The Alan Turing Institute is the UK National Institute for Data Science and Artificial Intelligence, and one of the objectives of the institute is to apply data science to real-world problems, such as what we're doing in the Vehicle Grid Integration Group, where we're trying to help modernize the transport and electricity infrastructure. So, without further ado, today's speaker is Dr. Marc Mültin. Marc is an authority on ISO 15.11.8. Marc co-authored the standard and developed widely used open source implementation of ISO 15.11.8 called RISE V2G. Please do leave questions in the text box for Marc at the end of this webinar, and I'm really looking forward to Marc's talk. Thank you, and Marc, over to you.
Great. All right. So you already gave a good introduction to the protocols, like front-end and back-end protocols. I want to build upon that and start with what I call the e-mobility communication stack. So at the very lowest level, as I see it, we have the IEC 61851, which, as you said, is a safety-related protocol. So the way this works is that the charging station and the car, they exchange pulse width modulation signals. This is an analog signal, which the charging station uses to tell the vehicle the amount of amps the vehicle can use to charge its battery. Based on that, ISO 15.11.8 is a high-level protocol, a digital communication protocol, which is used to control the charging process and where we can harness more information from the car, such as what is the needed amount of energy, what's the desired departure time, and things like this. Then we have the Open Charge Point protocol, which is the most widely used protocol to monitor and control charging stations. You already had a webinar session with Robert von Eihomer, where he explained in more detail what OCPP is all about. So it's not an international standard, but it's a de facto standard. However, since 2017, there is also an IEC standard called IEC 63110, which is called, as you see on the right side, Protocol for Management of Electric Vehicles Charging and Discharging Infrastructure. Its goal is basically to, well, have an internationally agreed upon standard on IEC level that is similar to what OCPP already does. Maybe they will extend it by some use cases, I don't know yet. Right now they are in the process of finalizing the use cases. The project team, which is doing all the requirements and the message definition, is still in the very early stages. But I think I've just seen that you have an upcoming webinar on 63110 as well with Paul Bertrand. Then on one level up, we have basically, we enter the roaming sphere where charge point operators and mobility operators. So charge point operators are the ones who are operating and monitoring the charging station, and mobility operators or e-mobility service providers, there are several words for it. They are the ones who provide the contracts for the end users to charge their car, the ones who provide RFID cards, for example. So these usually use roaming protocols in order to exchange necessary information for billing, exchange information about the kilowatt hours that had been charged and need to be billed, points of interest information is exchanged, and so on and so forth. And there we have protocols from Hubcheck, for example, the Open Intercharge protocol. We have eClearing.net's Open Clearinghouse protocol. We have the Open ChargePoint interface. So there's a lot of open protocols around already, which can be a bit confusing if you start out in this e-mobility world. All right, having said this, I would like to dive a bit more into the use cases of ISO 15118. So first of all, it tries to provide a very easy way of authentication authorization for the user. And ISO 15118 enables two ways of authentication. One is called external identification means, EIM for short. That is everything where the user has to, do an additional step in order to authenticate and authorize himself or herself. For example, presenting an RFID card to the reader at the charging station, or scanning a QR code with your smartphone, and SMS payment, credit card payment. So these all fall under EIM. The more user convenient and also way more secure way is plug and charge. And plug and charge enables security mechanisms on the transport layer. So it encrypts the transport, the communication layer with transport layer security. And we have XML-based signatures and digital certificates on the application layer. All right, it's a very convenient feature. It's like a plug and play. You plug in and all the authentication, authorization, and also billing happens in the background without any additional action required from the user. So you have to sign up for an e-mobility contract, and then everything works like a charm. But as I said, you can also do ad hoc payment if you want with external identification means. So both ways are still possible with ISO 15118. And of course, the most important feature is, or one of the most important features is optimized load management for both AC and DC charging. So you can make sure that the car is charged in a way that it's comes with the least possible cost for the user or the owner of the car, or that you use the most amount of renewable energy available at the very moment or during the time that the car is connected to the charging station. And you can make sure that the charging is done in such a way that the state of health of the battery is kept at a very optimum. You can do fleet charging management. Imagine you have a lot of cars parked at the parking lot of your employer. There you can have some very interesting fleet management scenarios, charging scenarios that you can employ there. Grid services, which we'll see in a second, and also the renegotiation of the charging profile, meaning at the very beginning, the EV in a charging station exchange some technical parameters, and then they negotiate on a charging schedule, but this schedule is not fixed. It is flexible so that the charging station can quickly react upon unforeseen changes in the grid. For example, we have an unforeseen huge load, or we have a lot of renewable energy, like a lot of wind currently coming up. So the charging schedule can be adapted throughout the charging process. Also, we have what we call value-added services. They are not specifically defined what value-added services there are, but it's more of a means provided to anyone who wants to employ value-added services. So basically, ISO 15118 allows you to exchange information via a separate communication channel that is provided via an FTP or HTTP or HTTPS channel. Then the next three features: wireless power transfer, bidirectional power transfer, and what we call ACD, which is automated, or stands for automated connection device. They're all features that come with a new version of ISO 15118, the -20, which will be available as an international standard very likely at the end of 2020. Automated connection device, for those who have never heard of it, One use case is charging buses via pantographs. Another use case could be like robotic arms, or like a robotic arm that is plugging the charging cable automatically into the plug of the vehicle, which is a very interesting use case, especially for autonomously driving cars. Let's have a look at how ISO 15118 compares to other standards in the market. I'm not sure if every one of you have heard of DIN-SPEC, which is listed here in the first row, DIN-SPEC 71221. This is basically a subset of an early version of ISO 15118, which only covers DC charging. The idea was back then, well, ISO 15118 started out in 29, and it was finished, or the main work started in 2010 and was finished in 2014. But in 2012, DIN-SPEC was released because the people who were standardizing this protocol thought, well, we don't want the DC market to be delayed by another 2 years. We want to have a standard you can rely on right now. So what they did is they took the DC part of the ISO 15118 specification that was ready back then in 2012 and released it as a German specification, which now has also become kind of a de facto standard throughout the world right now. But it was always supposed to be only an interim solution until ISO 15118 was released as an international standard. So then we have CHAdeMO. You all know CHAdeMO coming from Japan. This is also focused on DC charging, but in addition allows bidirectional energy transfer. So these V2G use cases and the V2G projects we see currently going on in France, UK, and other countries, they're usually CHAdeMO cars like the Nissan Leaf, and so far ISO 15118 does not cover bidirectional charging, the -2. We will have a look at the family or different sets of documents that ISO 15118 is comprised of. The most important part is -2, which was released in 2014, and this covers AC charging, DC charging, security aspects with plug and charge, and of course the smart charging. And ISO 15118-20, which will be released by the end of next year, covers all use cases you can think of. It comes with bidirectional charging, it comes with wireless charging, with ACD charging. And it's not only limited to cars. ISO 15118 serves all use cases to enable a seamless market introduction of all kinds of EVs, be it cars, be it buses, be it trucks, bikes, even ships or airplanes. At the end of October, like last month, ELAT hosted the first Char-In festival, where I can show you a video at the very end of this webinar if you have time, but I'll show you the link for sure, where we, for the first time, had a small airplane and even a truck and a bus to charge with ISO 15118. So this is quite amazing, I think. All right, let's have a look at the ISO 15118 family. I think with regards to the comments that will come in, I guess we're going to answer them at the very end of the after the presentation, right? Okay. So in total, there are, I think, 9 documents that ISO 15118 is comprised of. When you talk about machine-to-machine communication, then you talk about the 8 different layers of communication. From at the very bottom, we have the physical layer, and at the very top, we have the application layer. So the -1 document is covering the general use cases and all the information. So basically, it's a use case document. So if you want to know what ISO 15118 is about without diving too deep into the technical specifications, -1 document is the one to go for. The most important one is -2, which is called Network and Application Protocol Requirements. And this covers all the layers from the network layer up to the application layer. And it builds upon standard internet protocols, but also defines a little set of protocols, proprietary protocols on itself. So on the network layer, we use IP because it's a TCP IP-based protocol. And SLAC, which is short for Stateless Address Auto Configuration and Dynamic Host Configuration Protocol. Then we have a UDP, TCP, and for the encrypted version, we have TLS on the transport layer. So there's nothing new. It's all basic internet standards. And then we have the vehicle-to-grid transfer protocol, which is a small, very simple protocol, which is placed on the session layer so that the charging station and the EV know how to process the information that is coming in. All messages are defined as XML messages. XML is short for Extensible Markup Language, which is a machine-readable language, but it's also, but we humans can also read it. And XI is short for Efficient XML Interchange. You can think of XI as kind of a binary XML. So it reduces the amount of data that is sent over the charging cable, and it also speeds up the processing of the incoming messages. And then on the very top, on the application layer, we have the so-called V2G messages. So that's where all the messages that are defined, which we will go over in this message sequence in a few minutes, are defined. All right, so this is all -2, right? And there's also a -3 document, which covers the very lowest levels of communication, the physical and data link layer. There's also a tight relation to the IEC 61851 standard. Then we have conformance tests, which make sure that vendors in the market who implement these protocols can make sure that they are interoperable to each other and conforming to the standard specification. So there's a huge set of positive and negative test cases defined, and this is all written down in the -4 document for testing the -2. There's another conformance test document which covers all the use cases for -3. So this is the -5 document, which you see down here. There used to be a -6 document back then when we started to open up a new edition of ISO 15118, which covers wireless charging and bidirectional energy transfer and all the like. But a decision was taken to merge all the new use cases into a second edition of -1. So there's no -6 document anymore. It's -1 edition 2. So similar to the -7, this used to be the document which holds all the technical requirements and the new messages we need to enable wireless charging and bidirectional energy transfer. But it was decided to put it into a different document called -20 now, for several reasons, which I don't want to go into much detail because it's not very relevant for this presentation. We not only have conductive charging using, or conductive communication using the wireless, the cable, we also have wireless communication using IEEE 802.11n. So that's also a well-established Wi-Fi standard. And of course, we need a conformance test for the -8 document as well. So all in all, this is the complete set of documents. It can be a bit overwhelming at first, but you don't have to know everything. Of course, the most important documents are the -2 and the -3. That's where it gets very interesting. -2 and the -20, I mean. All right. The -20 is the one which enables vehicle-to-grid, the bidirectional energy transfer, so we can use the car as an energy source, stabilize the grid, and also power your home when you are in emergency situation, for example. All right. When we talk about vehicle-to-grid, we also need to talk about grid codes. What is a grid code? Well, a grid code or grid codes are technical regulations that any generating device connected to the grid needs to comply with in order to guarantee a stable and safe operation of the electrical grid. And these grid codes include voltage regulations, power factor limits, which usually range in the area between 0.9 and 0.95. Power factor ranges from 0 to 1, theoretically. Also regarding reactive power supply and response to short circuits and frequency changes on the grid. These are all regulated by grid codes. Now, this power factor might be a hard term to grasp at first. Let's try to explain it with a glass of beer. So imagine you have this beautiful big glass of beer, and for the beer you need both. You need the actual beer you can drink, but a beer without a foam is actually quite boring, right? So imagine now, or have in mind that power factor is the relation between active power and what we call apparent power. So the active power is the usable energy for the device. For example, the usable energy for the car to recharge its battery. That is the yellow part of the beer. The reactive power is the foam part on top of the beer. Reactive power is kind of like, you could say, wasted energy or wasted electricity, because you don't really use it to power the device, but you need it in order to ramp up the voltage and to get the whole AC system running. And both combined, the active power and the reactive power, is what you call the apparent power. So the relation between active power and apparent power is the power factor. And usually we want to have the power factor as close to 1.0 as possible. Okay, I hope I explained that well. All right, how do we handle grid codes in AC charging versus DC charging? So I have this image here, so we are all on the same page related to the terms we use with all the equipment here. So on the charging station side, we have the socket outlet. On the vehicle side, we have the vehicle inlet. Then we have the plug, which you put into the outlet. We have the connector you put into the vehicle inlet. And then for DC charging, the power converter is located off-board in the charging station. So the location-dependent grid codes can be programmed into the controller of the charging station, which manages the power flow from and to the grid. So since the charging station does not move around, it's usually located fixed at one location, you can, as I said, program these grid codes into the charging station, and no additional grid-related information needs to be exchanged between the EV and the charging station. In the AC charging case, you have an onboard charging unit inside the electric vehicle, and that is the power converter that manages the power flow between the car and the charging station. So here, technical requirements are needed to clearly specify the information that is exchanged between the EV and the charging station. So vehicle to grid with AC charging is a bit more complicated than with DC charging, because we need to make sure that the car is feeding energy back into the grid in such a way that the grid is still operating in a safe and stable way. All right, so how does ISO 15118-20, which is a new version, handle this grid code related AC charging? First of all, you need to know that ISO 15118 is a client server-based protocol. The client is the electric vehicle, and here we talk about the electric vehicle communication controller, the EVCC, and the server is the charging station, where inside you have a communication device which is called the supply equipment communication controller. So the EVCC and the SECC, these are the two entities that exchange information during a charging session. And the SECC can trigger certain request messages by setting a flag in the response message, for example, to renegotiate a charging schedule. But the request is always initiated from the EV side. So the electric vehicle sends a new message at the latest every 60 seconds. And the charging station responds within 2 to 5 seconds, depending on the message. There are timeout values defined for each and every message. And for the most part, the charging station needs to respond within 2 seconds. The car usually sends one request after another within hundreds of milliseconds. However, there is a timeout defined to know, so that the charging station knows whether or not the car is still alive, basically, or still awake. And that timeout is set to 60 seconds. But that doesn't mean that the car will only send subsequent messages every 60 seconds. That is very unrealistic. It's much faster. So in order to go through the messages here, I've presented you with a message sequence diagram. I'm going to go through different components now step by step so you don't feel overwhelmed. First of all, we have different states that relate to the IEC 61851 specification. And if you look on the left side of the diagram, which is tilted by 90 degrees, there you see a little legend stating state A, state B, state C. These relate to certain voltage levels and have a certain meaning. Namely, state A means no car is connected to the charging station. State B means the EV is detected, but it's not yet ready to charge. And state C means that the EV is detected, so it is connected, and it is ready to charge. Then we have the controllers on the EV and the charging station side, which handle this IEC 61851 specification. And we have the communication controllers themselves, the EVCC and the SECC, and of course the request and response message pairs that will exchange during this charging sequence. Right, so I'm not going into too much detail what each and every message is supposed to mean and how it works, but I'm going to give you the quick version of it, the quick walkthrough. So once the charging station or the car is connected to the charging station, they will establish a TCP/IP-based communication link. Then they will agree upon a commonly supported communication protocol. This could be ISO 15118-2 or -20 or even DIN-spec. This is all enabled using the supported app protocol request response message. That's the first message pair you see here in the sequence. Below that is a session setup request response message pair, which is used to negotiate a charging session ID. Then the EV will ask the charging station which services it offers with a service discovery request and response message. These services include value-added services, but also identification-based services like EIM and plug and charge, and also charging services. So these charging services include AC charging, DC charging, what we call WPT, which is wireless power transfer, and also ACD, which is short for automated connection device. And for AC and DC charging, we allow bidirectional power transfer in ISO 15118-20. Then there's an optional service detail request message that the car can use in order to get some more detailed information about a specific service it selects. And then the car will tell the charging station which identification service and which power transfer service it will use for this charging session now. So let's assume the car will use AC charging with bidirectional power transfer. So vehicle-to-grid charging is now possible in this charging session. You also have a message which is called certificate installation. You see here at the very bottom of this message sequence. This is in order to install a specific certificate the car will use in a plug and charge use case in order to automatically authenticate itself to the charging station. This certificate update message you see here is only relevant for the -2 version of ISO 15118, which was published in 2014. This is not relevant anymore for -20. This has been deleted. This is a little error in my diagram here. Then the car will authorize itself to the charging station. There is an authorization setup message and an authorization request. But let's skip that detail for a moment and go to the message called charge parameter discovery request and response. This is where the EV and the charging station exchange their mutual charging limits, and where the charging station can send a charging schedule to the EV based on external factors like a pricing signal and grid limitations, and also the technical limitations communicated by the car with a request message. So all this information, it's a very big data structure, but this is where the EV can send, amongst other information, what is the target energy request, what is the maximum energy request, and what is the minimum energy request. This means, what is the energy the car needs to fully charge the battery? This would be EV maximum energy request. But it's also possible for the user to set a specific state of charge he wants to charge his car to. Let's say charge only to 80%. So the delta between the current state of charge and the target state of charge is what is called here the target energy request. And there's also a minimum energy request, which is like when the user says, well, I want to charge a car and it needs to be charged, the minimum state of charge should be, I don't know, 50%. So that is the absolute minimum energy request. And also, what is the maximum charge power and charge current, and what is the maximum discharge power and discharge current? So this is very useful information in order to enable the vehicle-to-grid use case here. The charging station then, EVSE stands for Electric Vehicle Supply Equipment, which is a term usually used in the standard to relate to the charging station. So the EVSE sends then what is the maximum charge current, what is the nominal voltage, and what is the nominal frequency. And also what is the maximum discharge current. So what's the maximum current the charging station can provide to discharge energy. So this is all necessary in order to negotiate the charging profile, whether it's for AC or DC or bidirectional or not bidirectional. This charge parameter discovery is the essence to start a charging process, because that's where all the technical parameters are exchanged. Then we have the power delivery request. This is where the EV sends its calculated charging schedule back to the charging station, so that the charging station is informed how the EV will charge or will draw or provide energy over the period of time that it is connected to the charging station. So here we have a certain forecast that of course can change over time based on renegotiating the charging schedule, for example. But at least the charging station now has a means of planning the charging process. And if you imagine like a lot of cars providing this piece of information, then you can really do smart charging at large scale. Then we are in a charging loop. So we're actually delivering energy to the car, or if you're doing V2G, then the car is providing energy to the grid. And while this energy transfer is taking place, we exchanged messages, and in the -20 charging loop for AC charging, this message is called AC charge loop request response. It's basically, as a message pair to make sure that both partners are still, alive in the charging process. It's kind of a keep alive message, a control message, and provides means for the charging station to also renegotiate the charging session. All right, here the electric vehicle sends again the charging parameters it already sent in a charge parameter discovery, but they are updated throughout the charging process. So the values that the EV sent during the charge parameter discovery request are, let's say, the bounding values, and within these values it can reduce these fields or the values for the fields you see here on the right. And what you also see here at the very bottom of this list of information is the EV present active power and EV present reactive power. So these two fields are only sent if the car is doing V2G, like providing energy. And the charging station sends the target frequency, the target active power, and also the target reactive power. So the car or the charger inside the car can adapt to these control values sent throughout the charging session. All right, so when can we expect ISO 15118 cars in the market? Well, there's a lot happening right now, especially in 2019. Maybe let's start at the very right of this picture. You see the smart electric drive. This came to market in 2017, at least the version 3, which is capable of ISO 15118 and plug and charge. But they didn't really actively propagate the new feature because the infrastructure that we need in the background to make plug and charge work was not yet ready. For that, you need a lot of actors and a central platform which is taking on the role of providing certain certificates to the car and charging station. But we'll get to that in a minute. The Porsche Taycan and the Audi e-tron are quite famous cars that now come to market, and they will come with ISO 15118 support as well. I'm not sure if they will manage it until the end of this year, or if it's if they ship ISO 15118 in 2020. I'm not completely sure, but I'm sure they will. They are actively testing now with, for example, Ionity charging stations. Yeah, BMW, I don't know. I haven't heard anything from their side when they will come with ISO 15118 support. However, their BMW i3 came to market in 2014, and as I heard, you can, calculate with, let's say, 6-7 years of a new release cycle. So expect BMW to come to market with their new electric car, be it an I don't know what they call it next. I think that's iNext or something. Probably 2020 or 2021. VW, they come to market now with their ID3. However, as far as I heard, ID3 does not yet ship with ISO 15118. They may update them, but it's not going to happen in 2020, as far as I know. Hubject is a company, a joint venture of several companies, Bosch, Siemens, RWE, EnBW, Daimler, and BMW. They were the original founding companies. And now VW is also one of the shareholders. They provide the public key infrastructure as an ecosystem to make plug and charge work. And public key infrastructure is something we're going to look at in a few minutes. On the charging station side, Energy SE is a pioneer on the charging infrastructure side regarding ISO 15118 because they were the ones back then under the name RWE who invented ISO 15118 together with Daimler. So naturally they are one of the first on the market with ISO 15118 support. However, others are gaining momentum. For example, EB and Bender. Those two companies collaborate in selling their chargers or charging equipment, and they already have a very mature ISO 15118 implementation, as far as I know. If you register from my newsletter, you will get a market overview where a lot of companies already registered their products as ISO 15118 compatible or capable. And there's also the possibility to register your product. Just go to my website on the landing page. At the very bottom, you see the newsletter part where you can sign up, and there is a link where you can register your product. And this will benefit everyone in the market. All right, there are regular industry events where you can see the state-of-the-art development of ISO 15118. They started back in 2014, and since then we had, I think, 12 so-called ISO 15118 testing symposia, and now it's split up a little bit. We have now what is called a CHAR-in Festival and also the testing symposia. So the next two upcoming events, and I highly, highly, highly recommend you to attend either one of those, because it's the most most important industry event in the ISO 15118 domain. The next one is in ISO 15118 testing symposium in Stuttgart in May 14th and 15th, hosted by Vector Informatik. These are primarily going to be controller tests. They're not real charging stations and not EVs, but the controllers that go into the charging stations and the EVs that enable 15118 support. And I think the plan is now that these testing symposia are focusing more on the new developments. So the ISO 15118-20 will be tested at these events probably by the end of next year, because these are usually biannual events. They take time twice a year. And another very interesting event is the Char-In Festival. The first Char-In Festival happened in end of October in Arnhem, hosted by ELAT. The next one is happening in April, end of April at the 28th and 29th, hosted by Lucid Motors in California. This is going to be a really interesting event. I'm going to show you a video at the end of the webinar to get an idea of how these events look like. So at the very end, a few words to cybersecurity. Well, as I said, ISO 15118 also focuses on cybersecurity to enable this very user-convenient plug-and-charge feature. When we talk about cybersecurity, we need to tackle three pillars of IT security: confidentiality, integrity, and authenticity. So confidentiality means that the content of a message, which is, let's say, the plain text, shall only be readable by the intended recipients, but not by any other party that might eavesdrop on the communication channel. Integrity means that an unauthorized modification of a sent message shall be either avoided or at least be detected. And authenticity means that you can assert that the communicating parties are really the persons or entities in terms of machine-to-machine communication, which they claim to be. And these are all goals that we reach with ISO 15118. Confidentiality is enabled through the secure exchange of information to calculate symmetric keys, which we need to encrypt the information, through what is called elliptic curve Diffie-Hellman. All the cryptographic information I'm going to shortly highlight. If you're not a cryptography expert, don't worry. It's not easy to explain it within 5 minutes. I can do it. But I have more information on my website, which I'm going to show you, where you have enough time to look into it a bit more. But we need symmetric keys to encrypt information, and there we use Advanced Encryption Standard, AES, with the 128 cipher block chaining mode. Maybe the next slide is a bit more easy to comprehend or to digest. So ISO 15118 uses a hybrid crypto system approach, which means we have both asymmetric and symmetric crypto algorithms in place. The asymmetric part is where elliptic curve Diffie-Hellman comes in place, which we need as a secure way of calculating a symmetric key without explicitly exchanging that symmetric key. So in order to encrypt the information on both sides, you use a symmetric key, which means the key which is used to encrypt the data is the same as decrypting the data. But in order for the car and the charging station to securely exchange that symmetric key, we need a mechanism. And this is called, or the algorithm is called elliptic curve Diffie-Hellman. So this Diffie-Hellman algorithm has been invented in the, I think, late 70s by two mathematicians, Diffie and Hellman. And it is now based on what we call elliptic curves. So this symmetric key is used to encrypt all information with AES 128 CBC. So the ISO 15118 messages that are exchanged during a TLS session, they are all encrypted and decrypted using that symmetric key. And also, I was telling you about a digital certificate that is called a contract certificate that needs to be installed into the car so that the car can automatically authenticate and authorize itself to the charging station. there needs to be some way to install that certificate into the car. And this is also defined by ISO 15118. And next to that certificate, the private key that relates to that certificate also needs to be installed into the car. In order to securely send it to the car, it needs to be encrypted. So this symmetric key, which is exchanged here, or the elliptic curve Diffie-Hellman algorithm, is also used to encrypt the private key for the contract certificate and then securely send it to the electric vehicle. We also have a mechanism called elliptic curve digital signature algorithm, which is used to both create digital signatures and verify digital signatures. So this is pretty much state-of-the-art cryptography that is used in ISO 15118, which has been defined back in 2014, but it's still valid as a secure mechanism. All right. There is this image you see here on the right is the most complicated image in the whole standard, I would say. What it tries to convey is a set of digital signatures that need to be in place for the whole plug and charge system to work. They all relate to different market roles. On the left side, you see market roles like the charge point operator, the mobility operator, and the car manufacturer. And for each public key infrastructure, you have one dedicated market role, here color-coded on the right image. Another role which comes into play is the certificate provisioning service, which is needed to safely provide the contract certificate and the private key to the electric vehicle using the charging infrastructure or the backend telematics service of a car manufacturer. I'm not going into too much detail because we don't have enough time for that. Just that you know, there's a set of certificates that come with a public key infrastructure that need to be in place for the whole plug and charge system to work. And it already is working thanks to a company called Hubject, which has stepped up and provides a lot of roles that we need for the PKI infrastructure to work. I'm sure Hubject will not remain the only provider in this market, but it's the first one, and it enables for now how ISO 15118 cars can do plug and charge in the field. I think I'm gonna skip this one because it's not too important. The last part of my presentation is about available resources to get started with ISO 15118. So as I said, there is a list of market vendors that have already registered. They followed a call that I published a few months ago. And there you see from all over the world different kinds of companies that provide either a charging station or an electric vehicle or the controller or a test system or a PKI infrastructure. So all the elements we need within the ISO 15118 domain. And you can still register. If you think you have a product that is not yet listed on this list, please do so. Go to this link which you see on the slide and register yourself. And for all those who want to have this list, simply go to my website, register for the newsletter. I have a bi-weekly newsletter, and I make sure that I really only post something if it contains valuable information. There is no spam guaranteed. Okay, so there's also an open source implementation of ISO 15118 available. It's called RISE V2G. I've implemented it myself. It is a work that has been developed over many years. And since 2015, I think, I published it on GitHub. And ever since, it has evolved as a very how do you say, highly appreciated solution for companies across the globe to test either their already existing charging solution, either on the EV side or the charging station side, or even to use it to jumpstart their own charging stations. The RISE V2G covers the -2, which was published in 2014, and it covers all features of ISO 15118: AC charging, DC charging, both authentication modes, EAM and plug and charge, TLS with all the certificates handling and all the complicated cryptography that comes with it. It's implemented for both the EV side and for the charging station side, and it uses open source projects for the XE, the efficient XML interchange. So there are two open source libraries called XEfficient and OpenXE, which are shipped with RISE V2G. It's licensed under the MIT license, which means you can do anything you want with your code. With that code, you can use it in your own products. There is no copyleft license here, so there are no worries come with it. And another announcement I want to make, the -20. I will continue to work on ISO 15118. I'm still a very active member of the standardization body, and I will use my knowledge to keep ISO 15118 open source. So there will be a RISE V2G 2.0, or however I will call it, which will come with ISO 15118-20. The RISE V2G is so far implemented in Java, which is a reason for not applying it in the electric vehicle, but some charging station vendors use it in their charging infrastructure. I'm thinking of maybe doing it, the -20, maybe implementing it in Python instead of Java. Let's see. All right, maybe we quickly switch to my website, because there you'll see Knowledgebase Articles. Wait, wrong link. So if you go to my website at v2g-clarity.com, there you see in the menu up there Knowledgebase, and there I have a few deep dive articles. What is ISO 15118? What's the basic of plug and charge? So here you'll also have a deeper explanation of the cryptography that's in place, asymmetric and symmetric cryptography. What are the certificates that are in place? How does TLS work? And so on and so forth. This is all for free to get you started. And yeah, so far the information for the Knowledgebase articles. I also have published an ebook called the ISO 15118 Manual, which has become pretty much a standard literature for in the complete industry of car manufacturers, charging station vendors, solution providers. So the idea is here to provide a more easy access to the ISO 15118 standard, because the standard itself is a bit hard to read and understand if you haven't been part of the standardization body. The whole standard, or -2 alone, is 350 pages long. So I wanted to provide a means of an easy access to really explain how the whole standard really works, why things have been decided the way they were written down, and also helping you to avoid common pitfalls you can run into when trying to implement ISO 15118. So it's a book for both beginners and experts. All right, I also have some online courses available if you're interested here. And that's basically it. That's the end of my presentation.
Thank you so much, Mark. That was excellent. Did you mention you wanted to show a video?
Right, exactly. So let's go here. Wait, how do I? Oh, God. If you wait, I have it open here. Yeah. So the first RISE festival started in Arnhem this year, in the Netherlands. So the URL 2019.shine-festival.com. There you can see a very nice video from the last event. I'm going to show you quickly. Wait, but can't. hear the sound, right? So I'm gonna leave it at this.
Okay,
Go to
maybe
this URL.
You're providing the slides, correct?
Yeah,
So we can add a link to it.
exactly. I think that's the
Great.
best.
Great. Okay, so I can see questions starting to come up. But before I take some of the public questions, I just want to ask you one myself. There are 9 parts of the protocol, and some of them, okay, are conformance tests, and the most important ones are edition 2 and edition 20, and you have a manual that help people with them, but still there's a lot there to get to understand. And it's not just ISO 15118, there's also a lot of other protocols that we need to deal with between the charging station and charging operator. Someone that's just starting, a new player, how can they get around all these protocols? Where do they start? And if a protocol is not yet available, like for example IEC 63110, how can they wait?
Well, it also depends which role you take in the market, right? And no one needs to know everything except you want to explain it to the market. So I try to build up as much expertise as possible. I'm also a member of the Open Charge Alliance. I have been also actively writing parts of the OCPP 2.0 specification, and I'm implementing OCPP 2.0 right now. So I also plan to provide either a few articles or maybe even an ebook on OCPP 2.0.
Implementing it is making sure we can have something working between ISO 15118 and OCPP?
Yes, exactly. Oh, my OCPP implementation will very likely not be open source. However, the knowledge I will gain during implementation, I will use to provide freely accessible information to make it easier. But let's say, having this slide here open, you see all these different documents. If you're really interested in the technological aspect of this protocol, the -2 and the -20, those are the interesting ones. The -2 you can already buy. The -20 is right now in development.
And when you say buy, it's not very expensive, because we're here advocating open and universal protocols.
I mean, the ISO, the International Standardization Organization, is the one that sells it.
Yeah, but
I think they sell it.
That will prohibit a new company, a startup company, from buying it and trying to implement it.
No, it's open. No one. No, we want the full market to implement it. There's no restriction to getting it. Yeah. You just have to pay.
Okay.
I think it's between 100 and depends on the version. I think the prices they vary between 100 and a few more €100, I think.
Okay, so that's fine. That's fine. That is accessible for the
company. And OCPP 2.0 is free of charge.
Yeah, yeah.
I'm not sure if you have to be a member. I don't think so. I think it's free of charge.
Okay. Okay. In 2025, do you see that, at least in the EU, as a minimum, every single electric vehicle and charging stations are implementing ISO 15118 to allow this interoperability?
In the EU in 2025, you said?
Yeah, I mean, we've seen your slide with showing some car companies are planning to include this, but I wanted to get a feel of the maturity of the market, or the market penetration of this key protocol. When do you see that, as a minimum, electric vehicles and charging stations are implementing this protocol? Is there an alternative?
In Europe, there's no alternative.
Okay.
No. I mean, I have presented the other alternative, CHAdeMO. So right now, worldwide, we have basically 3 major standards. The CCS, which is the combined charging standard, which where ISO 15118 is part of it. Then we have CHAdeMO, which is primarily used in Japan. And of course, we also still have a lot of CHAdeMO chargers in Europe and in the States, because they were the first chargers around before CCS chargers came. But as far as I know, their number is decreasing. So CCS has a very strong lobby, and they are really increasing their installation base. And third, we have the GPT standard, which is the Chinese standard, but that is only relevant in China and nowhere else. And even in Korea, they adapted CCS now, as far as I know. I think India is also adapting CCS, so they are gaining a lot of traction in the Asian market. And especially in Europe and in North America, CCS is basically set. So 2025.
Can you remind people the link between ISO 15118 and CCS, please?
So CCS is the set of hardware and software standards that are covered under CCS. So CCS defines that for DC charging, you can use thin spec and ISO 15118, depending on which version of CCS. And then that you have the combo 1 and a combo 2 version of the socket. Maybe I have a very nice slide on that. Give me a second. The other right. Okay. So you see this inlet here, the combo 2 inlet in the middle.
Yeah.
Of the slide. So that's the CCS inlet you see at the electric vehicle. The upper part is the interface you see at the which correlates to the type 2 AC inlet and socket.
Yeah.
And the lower part here is the specific DC or dedicated DC pins for the DC charger.
And that's what makes the combo.
And that's exactly, and the complete interface is called the combo. Combo 2 because of the type 2 interface, but there's also combo 1 for the interface used in the United States. Okay.
Great. Thank you.
So
yeah.
Yes, I think by 2025, that's probably a very realistic date. I think that at least every new electric vehicle will come with ISO 15118 support, and every new charging station should have ISO 15118 support. Everything else would be at least for the charging infrastructure side, a waste of investment, because if your infrastructure is not ISO 15118 ready or capable, then it's basically a dead investment, because you have to exchange hardware, and that can be very expensive.
Okay. We're talking in Europe.
Yes.
Okay. Great. Okay. I received some questions privately, so I'll read those first, and then I'll let you take the ones that are available to everyone. Okay. So someone mentioned, which I think maybe it's not true, but they understood from the presentation that the battery size, the VIN number, and state of charge will be exchanged, as well as how fast the communication is. Example, support very fast reaction grid services like synthetic inertia. My understanding is no, state of charge will not be exchanged.
It depends.
Okay.
First, you need to distinguish between -2 and -20.
Yeah.
In -2, for DC charging, the state of charge is exchanged. I'm not sure if it's an optional or a mandatory value. That I would have to look up. But in AC charging, the state of charge is not exchanged.
So in AC, not.
In AC, no.
But in DC, it is optional.
Yes.
However, you mentioned that some energy values can be exchanged. So even though the state of charge is not, there's still some valuable information that can help with the strategies, right?
Yeah. Yes. So the state of charge is not relevant for a smart charging strategy. What you need to know is the amount of energy the car needs and when the car is supposed to leave, because that's a piece of information that the user provided via the human-machine interface in the car, the head unit.
And is information optional or mandatory?
No, that is mandatory. That's absolutely mandatory, because otherwise you cannot do smart charging.
What about battery size?
No. That is something, so the battery capacity, that is something that will come in -20. We just have discussed it last week in a standardization meeting. but also as an optional value.
Okay.
So there's a set of values called display parameters, amongst which we will see state of charge and battery capacity, I think. But these are optional. There have been very intensive discussions going on. A lot of people like them to be mandatory, but the OEM side wants to keep them optional.
Are you able to share insights on why they want to share that, keep them optional?
Well, one of the reasons is GDPR compliance. If a car owner does not want to share these details, they must make this possible so that the user can, hinder sending this information, because some just may not want to share the information. So that's why it's optional, which doesn't mean that this information will not be sent. It's just you cannot rely on it.
Okay, that means also the VIN then must not be mandatory. So the vehicle identification number.
No, this will probably not be sent. I mean, in a plug and charge use case, there is a certificate in the car, which is very unique to each and every car.
Okay.
And this certificate has a unique identifier.
Okay.
This is the structure of that identifier is very close to the vehicle identification number. This may be differently implemented. Once again?
So as long as we have something to uniquely know who is charging what?
No, there's a contract certificate in the car, right? And that certificate is related to the charging contract that you sign up for. That unique identifier will be sent each and every time you charge, because somehow you need to identify the user and bill him for the energy that has been delivered, right? So that identifier is sent each and every time you charge your electric car.
Okay. Are you able to see some of the questions?
Wait, let me open the chat. Yes. Okay, let's start from the beginning. From Rebecca, I just read a few days ago that Shademo will also support plug and charge. I don't know about that. Maybe you could share more information about that. They probably have also the idea of using certificates to automatically authorize the car, but I have not yet written or read any details about that. But it's likely. So Giacomo Cuneo, Mark, more a question for utilities, but you touched the PF.
Yeah.
The power factor topic.
Saying grid. Yeah.
Yeah. Touched the PF topic. Saying grid would request a min power factor of 0.9 or 0.95. Is it possible that the grid could specifically request sometimes a higher reactive power to keep the voltage high? Would it be desirable to have EVs producing energy also with lower PF? I must say I'm not an expert in that domain with power factor. So I guess it could be possible that the grid would also request a higher power factor. I'm not sure to which degree the car can respond to it. It also depends on the power converter in the car, right?
And maybe the charger as well, no?
Yeah, that's what I mean, the charger, yeah.
Yeah.
So the question is also, is there, let's say, a threshold that, let's say, the charging station will require a certain power factor, but if the car cannot meet that requirement, I don't think that the car will instantly be shut off. There will be a certain, let's say, threshold around it. Yeah, it depends on how hard that requirement really is. So Paul asked me, Mark, has ISO 50018 crypto architecture been subject to independent audit? If so, is there audit available? Yes, there was an audit, but this audit is unfortunately not available. Sorry, I also don't have it. There was a security task force in place a few years ago that came up with the architecture, but for some reason I have not gained access to it yet. So Paulie asked me, hi Mark, Audi has published its support for EEBus V2G energy transmission. Do you know if EEBus is supporting ISO 15098-20 standard, or has they invented some proprietary mechanisms, communication? I'm sorry, I have no information about EEBus. I know it exists, but I don't know if they consider 15098 at all or not. But I'll dive into it. It's an interesting question. Alexander says, Mark, firstly, I'm really glad to hear you and want to say thank you for your work. Thank you. Oh, that's a long text. Okay.
That's why I'm read it.
May you comment the situation that developers of DIN ISOstack cannot easily find and buy hardware for CCS? For now, basic hardware that I know is QCA700X from Qualcomm, but it is almost impossible to get documentation for it and create something with it without docs. How can we deal with the situation? How possible to widely adopt CCS if we cannot create our devices? In comparison probably with CHAdeMO, GPT, and new standard that China and Japan is developing together now, how will CCS survive if only thing I need to create CHAdeMO or GPT or this new competitor of CCS with backward compatibility to all CHAdeMO and GPT is simple standard with Canvas. With CCS, it is a pain and shortage of open source hardware. I'm forced to buy some already made devices and use only QCA700X chips. From my point of view, if they add anticipation of Canvas, then all CCS features can be adopted. Okay, let me share one slide with you. Wait, where is it? Here, somewhere. Here. So yes, Qualcomm is or has long been the only provider of home-plug GreenFi compliant chips, which you need for the low-level communication to establish the data link. They are the QCA 7000 or 7005 chips. However, there are other vendors in the market as well. As far as I know, they're called ST Microelectronics and MStar. I've recently looked them up. I didn't find much about MStar, but ST Microelectronics has a website where you can find out more, especially for the charging infrastructure side. And as a side note, my open source project RISE V2G only implements -2, which is starting at the communication layer 3, from the network layer up to the application layer. So that the ISO 15118-3 has not been my focus. There is a special communication mechanism called SLAC, which is short for Signal Level Attenuation and Characterization. I've skipped that so far, but I plan to dive into it and also implement SLAC myself and provide it as an open source project, because I also find it a bit of a, let's say, unlucky situation that we don't have an open source solution for SLAC. There is the OpenPLC utils project, which you find on GitHub. If you search for OpenPLC utils, this is a GitHub project where you have, come on, open up, where you have a project written in C, where all the SLAC messages are already defined, but the state machine for the SLAC procedure you have to implement yourself, I think. And I want to implement that as well, very likely in Python, and provide it as an open source project along with some good documentation, because SLAC can also be a pain in the butt as far as I heard. So this will help you maybe and others in the market. Not sure when this will be. I plan for, let's say, first half of next year. So this answered the question regarding to Qualcomm, if there are other vendors in the market. And yeah, I mean, CHAdeMO is a CAN bus-based protocol, which comes with some limitation, especially regarding bandwidth and security. So I would not go for a CAN-based protocol, but instead use a TCP-based protocol like ISO 5011 and therefore CCS. And CCS also now has the next version 3.0 comes with a new charging interface for a 2 megawatt charger to even be able to charge ships and airplanes and big trucks. So this is also a new initiative to further develop CCS. And I know that CHAdeMO and GBT, or the Chinese and the Japanese government, they want to collaborate to provide a common standard. So far, I have nothing seen. I've only heard that they want to do it, but let's see if they will come up with something useful. Okay, let's go to the next question. I hope I answered your question sufficiently. Hi, Mark. Are trouble codes for charging for both the EV and the meter covered by ISO 15118, or is there another standard for those? For meter, I'm not sure what exactly you mean here. Trouble codes, I mean, there are response codes in ISO 15118, a very big set of response codes that the charging station can send to the EV when something goes wrong during the communication. So the EV knows what went wrong. But related to meter or meter information, there's nothing specific in the standard, I think. So Alexander, hello, sorry for a typo in your name. Yes, there is, but the problem is hardware. I cannot create hardware itself, only buy it. No, these QCA or these home plug greenfied chips, I never try to buy them or do them myself. So I don't know, apart from these 3 vendors I listed, where you can get those chips. Yeah. Yeah, I think that's it for now. Do you have any more questions that you received?
Not on the side. I would like to thank you so much for your time. That was really excellent. Any parting thoughts?
Thank you. Any what?
Would you like to end with anything?
No, that's it from my side. I'm very happy that I had the opportunity to be part of your webinar series. Very nice.
Thank you.
Yeah, looking forward to the upcoming series.
Of course, and I hope we see you in the UK soon.
Yes, we will.
Good. Okay. Bye, Mark.
Bye-bye.